Okay, in this example, we're going to be looking at a slender bar which is bent at a right angle, and it's fastened to the wall at point A, and then at point B, it's not fixed to the wall. You can see there are these like little rollers there. It's against the wall, but in the vertical direction, it's not fixed. So there's no reaction force from the wall in the vertical direction, but there will be a vertical reaction force in the horizontal direction because the wall is going to be pushing back that way. And in this problem, we want to find the reaction force at point A, where it's fastened to the wall, and at point B, where it's pressing against the wall with these sort of rollers. So what are the reaction forces? That's the problem. And we're going to use the center of mass of the bar in order to calculate that. And we're actually going to do this two different ways. First, we're going to find the center of mass of each segment, and then we're going to find the center of mass for the entire bar. So let's look at one method for working this problem. We're first going to consider the center of mass of the horizontal segment and the center of mass of the vertical segment. We're going to consider them as separately. Later we're going to rework this problem considering the center of mass of the entire system altogether. But first of all, we're just going to find the center of mass of this segment and the center of mass of that segment. Why are we applying the center of mass? We want to find the forces that are acting at these connection points. Why are we bothering with the center of mass? Because this is an extended body, and we want to be able to deal with all the forces acting on this extended body. And the way that we do it is we can basically treat all the mass of this segment of the bar as acting here. So there's a weight of the bar which is entirely acting at the center of mass. And there's a weight of the bar here, which is also entirely acting at the center of mass. And then we have the reaction force at the fastening point A. So we have a horizontal component AX and a vertical component AY. And so that's going to be the reaction force at that connection point. And then there's a reaction force at this other connection point there, which is B. And you could call that BX because it's in the X direction, or just B, whatever you want. It doesn't really matter. But what we're going to do is we're going to apply our equilibrium conditions. We know the equilibrium conditions say that the sum of the forces in both the x and the y directions, z2 if you have one, but here we only have x and y, the sum of the forces all equal to 0, and then the sum of the moments about any point has to equal 0. That's necessary for this system to be in equilibrium. Now, we're going to pick point A as our axis of rotation because there's two forces whose force line of action intersect that point. AX goes directly through that point, AY goes directly through that point, and so those two forces will have no moment about that point. And so that's going to be something that will let us calculate the moment of the system in the easiest way possible. Now, the next thing that we want to do is calculate the sum of the forces. So if we do the sum of the forces in the x direction, the sum of the forces in the x direction are simply going to be AX, and we can see AX is in the positive x direction, and then B or BX is in the negative x direction. And so we can simply add them together and say AX minus BX is equal to 0. Next, we can do the sum of the forces in the y direction. Here we have AY, which is positive, the weight of the horizontal segment of the bar, which is in the negative direction, and that's going to be 40 kilograms times little g, and so 40 times 9.81, that's going to be the weight of this segment. How do we know 40? Because in the problem they told us the bar was uniform and it had a mass of 80 kilograms. That means this segment's got to be 40 kilograms and that segment's got to be 40 kilograms. Now, if we apply the sum of the forces in the y direction, we get AY minus the weight of the horizontal bar minus the weight of the vertical bar, all equals to 0. The only unknown here is AY, so that's actually pretty easy to solve for, and we get AY is 785 newtons. So we've done the sum of the forces in the x and the sum of the forces in the y. Now we want to do the sum of the moments about point A. Now I could do the sum of moments about any of these points, and point B would actually be a pretty good point too, because that force would have no moment and that force would have no moment. So you might want to try that just for fun and see that you get the same answer. And here's a hint, you should get the same answer. But anyway, we're going to pick point A. And so, as I said previously, AX and AY do not contribute a moment. This force, the 40 kilograms force providing a weight downward, acting at the center of this segment, that force line of action is going to be going straight along that line. And so the moment arm to the axis of rotation is just this half of a meter. Now, for this moment arm here, whose force line of action is going all the way down here, that force line of action is going to have a moment arm a perpendicular distance. So here's the axis of rotation. I go to the perpendicular distance to the force line of action, which for this force is vertical. That one's going to have 1 meter. And then for this B force, the BX force, its force line of action goes like that. And so its perpendicular distance to the axis of rotation is also going to be 1 meter. Now, these two guys, again, AX and AY, they provide no moment, no torque. This one, if I imagine this guy being hinged here and free to move otherwise, a force pulling down here is going to make it want to rotate in the clockwise direction. So if I just let this guy go and this force is pulling it down, it's going to swing down that way, and that's going to be a clockwise rotation. The same for this force. This force is going to, if this were the only force acting on it and it were hinged and free to move here, this guy would pull it down and it would move in the clockwise direction. So both of these forces are going to provide a negative moment. However, again, if it were hinged here and this were the only force, this BX were the only force, it would tend to rotate in the counterclockwise direction, which would be positive. So this force is going to provide a positive moment. These forces are going to provide negative moments, and those forces are going to provide no moments at all. So if I plug in all the moment arms, 1 meter times Bx minus 1 meter times the 40 times 9.81 newtons, that gives me the moment of 1 meter times 392.4. And then here we have the other force here, which the moment arm is only half a meter. We plug in the same weight, and we can solve for Bx. We get Bx is 589 newtons. We know that Bx and Ax must be the same, and so we have answered the problem. We can say that Bx and Ax are 589 newtons, Ay is 785 newtons, and so we have the reaction forces at both points A and point P. In this next slide, we're going to consider a completely different approach for working this problem. Previously, we already said that the centers of mass are going to be at the center of each of those locations. And so we're going to use the formula for combining centers of mass, which is just like the formula for combining centroids of lengths or areas or volumes. We have x bar times L1, that's the center of mass of bar 1, and remember that x1 is just a location, it's going to be half a meter, times L1, which is the length of the bar, and then this is going to be x2 times L2. Again, this is the x-coordinate of that center of mass times the length L2. And so if we put this guy here, we get 0.5 times 1 plus 1 times 1 divided by the total length, which is 2 meters, a meter here and a meter there. And so when you plug and chug, you get the x location for the center of mass is 0.75 meters. And then for the y location of the center of mass, you plug in the same values with y. And we can note that this guy has a y value of 0. This guy has a y value of 1/2. And we can see the lengths are both 1 meter. And when you plug and chug that, you get 1/4 of a meter. And so this 0.75 in the x direction, 0.25 in the y direction, that is the location of the center of mass of this entire bar. We've combined these two, and so that would be there somewhere. So we can say that, I go over about 3/4 and up about 1/4, that's going to be the center of mass of this whole system. Now note, it's in space. It's not actually on the body, but that doesn't matter. We can still apply the math, and the math works. So here we have our system drawn again. We have, again, the reaction forces at A, the vertical and horizontal components. We have the reaction force at B, and remember there's only the horizontal reaction force at point B. And then we have the entire object, which is 80 kilograms, and we're pretending that it's located right here. So this is the location of the center of mass. And so we can pretend all the mass of this object is located right there, or that the entire weight of the object is acting at this position. Now we can use that to find the moments at point A and point B. We can find the, not the moments, the reaction forces at point A and point B, and that's what we're looking for. We're looking at those forces acting on those points. Again, we're simply going to plug in the sum of the forces is equal to 0, and the sum of the moments is equal to 0. The sum of the forces is easy. The x has just got ax and bx again, or a minus b equals to 0. The sum of the forces in the y direction, we just have this one force vertically upwards and this one force vertically downward. And so we can plug those in. The vertically downwards, why that's minus. And then we can do the sum of the moments about point A. And again, if I pick point A as my axis of rotation, AX and AY provide no moment because their force lines of action go through the axis of rotation. This guy's force line of action has a moment arm of 0.75. This guy's force line of action has a moment of 1 meter. Remember, the force line of action is going left to right here, and the perpendicular distance from the axis of rotation is going to be 1 meter. So we can plug and chug 1 meter times B minus 0.75 times mg. That's the weight of the entire 80 kilogram bar acting at that point, all equals to 0. Again, positive and negative are determined by the sense of rotation. So if this is my axis, this force is going to tend to make it rotate clockwise, which is negative. This force is going to tend to make it rotate counterclockwise, which is positive. And so that's why the signs are what they are. And when you plug and chug, you get the same answers that we got before. Specifically, we see that AY is 785 newtons, BX and AX are the same, they're equal to 589 newtons, and that gives you the answer to the problem. And you can see there's two equivalent approaches for solving a problem like this, which is kind of nice. Now, this is obviously an example from your textbook. In the next slide, we're going to be looking at a sort of a practice problem that goes along with this one, as your textbook does not work out, but I thought it was tricky enough that I wanted to go through it with you because I think there's a lot of good content in solving it. So let's look at that now. This is basically the same problem that we had before, but instead of the bar being bent into an L shape, it's bent into this sort of circular shape. And so I have this circular shape, which is a quarter circle. It's fixed at point A. Again, we have the little rollers at B, so there's a horizontal force, but not a vertical force from the wall acting at point B. The bar is still 80 kilograms, and we want to know what are the reaction forces at A and B. In order to do that, what I'm going to do is I'm going to use the second approach that we used in the last problem. I'm going to find the center of mass of this whole segment, this quarter circle segment. We know it's 80 kilograms total. It's a uniform, homogeneous bar, and we want to find the center of mass of that, and then we can treat this entire bar as simply an 80 kilogram mass acting at that point. And so the fact that this is curved in a weird way doesn't really make the problem any harder. But finding that center of mass, that can be a little bit tricky, so that's what we want to look at. So what we want to find is a center mass of a quarter circle. I've got this figure that I've drawn turned in a more usual way. sort of right side up, just because I think it's easier to look at that way. And one of the things that I want to point out is that we can very often exploit symmetries to help us work problems. This is a uniform bar, and so we know that the centroid is going to have to be on this line of symmetry here, because basically the segment is a mirror image. You could fold it around this line of symmetry and it would fold together. So we know that the symmetry line y equals to x is going to be we know that the center of mass has to be somewhere on that line. So if we find the x coordinate for the center of mass, we've simultaneously found the y coordinate for the center of mass, which makes our life a little bit easier. So let's do that. Now, the formula for the center of mass is here. The center of mass is the integral of x dm over the integral of dm, and we know that the integral of dm is just the total mass. So that's going to be that 80 kilograms of the bar, which we'll plug in at the end. But what is x? It's easier to see that when we're dealing with circles, very often we have used the trick of switching to polar coordinates, and so that's going to be sort of a nice approach here. And so if I consider the position here, and I go straight down, and I could pick any radius, not just the one that's at 45 degrees, this distance here would be r cosine of theta. And of course, the vertical distance would be r sine of theta. And so if I want to do my integral over the variable theta, I need to express x in terms of theta, so that's just going to be r cosine of theta. And so that x is going to plug right into my integral up above. Now, the dm is what's tricky about this. Remember what dm is. It's the little piece of mass. We're breaking this into a little piece of mass, and it's equal to lambda times dl. That's our usual way of handling it when it's a line. And what is lambda? Lambda is the mass per unit length. So if I take the total mass and divide it by the length of this segment, which is pi r over 2, that's going to be the mass per unit length. That's the lambda. And so that gives me the lambda, and then the dl is just r d theta. We've seen that many times before, that if I have, a segment, if this is some d theta, and this is r, this segment is going to be r d theta. And so that gives me the length of the segment dl. And so my dm here is lambda times dl, which gives me this. And I can simplify this. I can see immediately that, for example, those r's cancel out. That r cancels out. And the 2 can flip up top. And I'm left with 2m over pi times d theta. That's the amount of the segment dm contained in a little arc of angle d theta. And so if I plug that into my formula, I get the center of mass is 2m over pi. Those are all constants, so they pull out of the integral. Now, hopefully it's obvious that my limits of integration are going to be from theta equal to 0 to theta equal to pi over 2. And so I do that integral, and it's pretty straightforward, and you end up with 2r over pi. And in our problem, we're told that the radius of the circle is 1 meter, and so that's just going to be a location of 2 over pi meters, and that is where the x-coordinate of the center of mass is. And so remember, that's 2 divided by 3.14, and so it's going to be less than 1, somewhere over here. And now we immediately know what the y center of mass is. And of course, if we wanted to, we could calculate that directly. We could say that the y center of mass is equal to the integral of y dm over dm, where y is equal to r sine of theta. And if you plug and chug that, I think you'll find that you get exactly the same thing. So what happens when you do this integral is you get some negatives that pop in, but they end up canceling, and it all works out in the end. So I suggest you try that on your own and see that you indeed do get the same answer for the y coordinate for the center of mass. Now, if we apply this to our original problem, we see that very similar to what we had before, the sum of the forces in the x direction are going to be ax minus bx equal to 0. The sum of the forces in the y direction are going to be ay. There's going to be that vertical force acting at y, and minus the weight of the entire bar, which is 80 kilograms, times the acceleration due to gravity, is equal to 0. We can immediately solve that for ay. Now we can do the sum of the moments. Again, we'll do the sum of the moments about point A. So the reaction forces at point A provide no moment. The reaction force at B, it's going this way. It's going to have a 1 meter moment arm, just like we did before. And then the moment of the other force, and so remember, our center of mass is going to be 2 over pi over, 2 over pi over, so it's going to be over here somewhere. And we can see that the moment arm is just going to be that distance because the weight is going down like this, and that distance is going to be the moment arm to our axis of rotation. And so when we apply that right here, that's just our moment arm times the weight of the entire bar, and we can solve that for bx, and we get bx, which we know from up above is equal to ax, and that works out to be 500 newtons. And so we actually see that the y value is the same as it was in the previous example, but the reaction force in the x direction is a little bit less because of this curvature of this bar. The next problem that we want to look at is one that involves volume. And in this example, we have a cylinder. It's a right circular cylinder of area A. So the cross-sectional area of the cylinder is A, and its length is L. And we can note that the base of the cylinder is in the YZ plane here, and that it's centered about the x-axis. So the x-axis is the central axis of the cylinder. Now the density is not constant. It's actually varying with the distance x along its length. And so if I plug in x equal to 0, so on this side at the YZ plane, if that's 0, then the density is just rho naught times 1, because that goes to 0. It's increasing as x increases. This value is increasing, so the density is linearly increasing until you get to the other end at the position x equal to L. If I plug x equal to L right there, I get 1 plus L over L, which is 1. And so that just gives me that rho is equal to rho naught times 2. So the density is linearly varying between rho naught on this end and 2 rho naught on that end. And so we would expect the center of mass not to be in the center, but shifted towards this further end, because there's more mass concentrated the further away you are from the YZ plane. Now, we want to calculate the mass of the cylinder to begin with, the total mass of the cylinder. And so what we're going to do is basically do an integral involving the method of disks from calculus. You guys probably remember that very fondly. I know everyone loves the method of disks and the method of washers. It's very fun stuff. So what we're going to do is break this larger cylinder into little thin slices, which are little bitty squat cylinders of width dx, and again it'll have the same cross-sectional area dA. And so what we're going to say is that the mass of the cylinder is simply the integral of rho over the dV. So I can consider, effectively, if my dx is infinitesimally thin, I can consider the mass of this to be constant, this slice, the density of this slice to be constant because the x is so infinitesimally small. And so I can calculate the mass of just this little piece of dV, which is going to be rho dV, Rho is mass over volume, so mass is rho dV. To get the mass of the entire cylinder, I want to integrate and add up all the masses of all the slices contained over the whole thing. And so I plug in my formula, rho naught 1 plus x over L. That is my rho. And then this second piece here, a dx, that's my dV. Because the volume of my little slice is going to have an area A and a height dx. And that's the formula for the volume of a cylinder of height dx and area A is just a dx. And so that gives me my dV. I've got my rho dV. Now it's just a matter of doing the integral. Rho naught and A, those are constants, so they come out. And also, let's note that our limits of integration hopefully are obvious, but they're going to go from x equal to 0 to x equal to L, the entire length of the cylinder. That's why we have those limits there. And so if I do this, I can separate this out and say this is going to be the integral from 0 to L of dx plus the integral from 0 to L of x over L dx. And when I do those integrals, I end up with the integral of dx gives me x. The integral of x dx gives me x squared over 2. There's that L in the denominator there. And so I'm left with x plus x squared over 2L from 0 to L. I plug in x equal to 0, I get 0. I plug in x equal to L, I get an L here. I get L squared divided by L there, and that leaves me with L over 2. And so I get rho naught A times L plus L over 2, or 3/2 L. And so I can simplify that, and I get an expression for the entire mass of the cylinder to be 3/2 rho naught A times L. Now we have the mass of the cylinder, we can calculate the center of mass. So we can remind ourselves the formula is going to be the integral of x dm, and of course this little piece here, that's my dm, so I've got x dm, or x times rho dv, divided by this guy. This guy is what we just calculated. That is the mass of the whole thing. So the denominator gives me the total mass that we just calculated, and so what we really need to do is just do this numerator here. And so that's going to be x times rho. So again, from there to there is rho. From here to here is dV. And so I've got x times rho dV. That's my x dm. And that's going to let me work this. Now this x here is going to distribute, and I'll end up with x plus x squared over L. And that's what I have here. So I've just taken this x and multiplied it through. And so now my integral is rho naught x plus x squared over L quantity times a dx. The rho naught and the a are constant, they can come out. But really what I'm left with is an integral of x plus x squared over L dx from 0 to L. And when you do that, the integral of x is x squared over 2. The integral of x squared is x cubed over 3. Plugging those in, I end up with this, and again our limits are from 0 to L. This is just the numerator, by the way, so we're just looking at the numerator. And when we do that, we plug and chug and we simplify, we get that the numerator of that expression is 5/6 rho naught A times L squared. So now we can combine our two results. We have the x-coordinate of the center of mass is x rho dV, which we just calculated, and divided by the integral of rho dV, which we calculated previously. Plugging those values in, I can see there's going to be a lot of cancellations. So we can see that the rho naughts are going to cancel, the A's are going to cancel, one of those L's is going to cancel with the L below, and so what I'm left with is just 5/9 L, and that is the position from the left side of the cylinder, how far up you have to go to find the center of mass. And of course we know by symmetry it's going to be on the x-axis, so the y-coordinate and the z-coordinate of the center of mass are going to be 0 just by symmetry. And so by solving for the x-coordinate, we've solved the whole problem, and that's where the center of mass for that cylinder will be located.